Okay, so for today we're going to look at the integration of exponential functions. We're going to look at basic rules and use substitution rules, and there'll be two of them. The first one is that the integral of e to the x with respect to x is going to be equal to e to the x plus c. That's the basic rule. And the corresponding use substitution rule that goes with that is that the integral of e to the u times u prime with respect to x will be equal to e to the u plus c. This should make sense because remember, differentiation and integration are opposite processes. So if I take the derivative of e to the x, I simply get back e to the x. And then similarly, we remember that when we differentiate, we add the u prime. When we integrate, we need the u prime. We also have exponential functions for bases other than e. The integral of a to the x with respect to x is going to be equal to 1 over the natural log of a times a to the x plus c. And that's going to be our basic rule, and our u substitution rule that matches that will be that the integral of a to the u times u prime dx is going to be equal to 1 over the natural log of a times a to the u plus c. And believe it or not, these two rules here are the same. The base e is just a special case of this one. And as a matter of fact, if you look at what happens here, if I use that rule for e to the x, that's going to give me 1 over the natural log of e times e to the x plus c. But what is the natural log of e to the first? Well, it's simply 1. And so that's how we get just a simple e to the x plus c on that one. So let's go ahead and look at some examples here, and we'll see how we integrate this stuff. I'm going to start by looking at the integral of a negative 3e to the negative 3x with respect to x. And here it becomes more important than ever that we understand the process. Again, the process is, if it doesn't fit a basic rule, and the only basic rule I have with an e in it is exactly e to the x, then that means I'm looking for a u substitution. And I have several choices of u once again. I can let u be the exponent, which in this case will actually work out nicely. U would be equal to a negative 3x. So the u prime would be equal to a negative 3. I could also, in some cases, and we'll see in later examples, let u be the entire exponential piece. We'll see that as we go. But as we started down this one here, again, what I'm noticing is that if I let u be the exponent, the u prime is a negative 3. And this turns out to be e to the u, and there is my u prime. And when I integrate e to the u times u prime, I simply get back e to the u plus c, which in this case is going to give me an e to the negative 3x all plus c. And as I've said before, folks, it's absolutely not okay to leave a negative exponent. However, because of the x in that exponent, I don't know that that exponent will necessarily be negative. It may indeed be positive. Because if x, for example, is a negative 1, then it's not a negative exponent. Kind of the same idea we had when we said, and let's do this little sidebar over here, that it's perfectly okay to leave me with the square root of x. But it's not okay to leave me with the square root of 9. In that case, you'd have to tell me that that was 3. Well, it would be okay to leave me with an e to the negative 3x, but it would not be okay to leave me with e to the negative 3, because in that case, I know that that exponent is negative, and I would want to make it positive. So again, when you have these things with x's in it, and you're not we can't tell, we can leave them in that format. Let's continue on here with some more examples. For number 2 here, let's try the integral of e to the 5 plus 2x with respect to x. And again, we go through the process. Not a basic rule, because the only basic rule that we have would have to look like exactly e to the x, and this doesn't. So I'm going to try a u substitution. Once again, in this case, I think letting u be equal to the exponent is going to work out quite nicely. If I let u be equal to 5 plus 2x, then the u prime that goes with that is 2. Well, looking back at this, I see that I have my e to the u here, and I just need my u prime. And remember, numbers are something we can get. If I need a positive 2, I simply multiply on the outside by the 1/2. again, anything on the outside is going to carry down. And even though I need the u prime in my work, it doesn't come out in the answer. What comes out in the answer here is just going to be the e to the u plus c. Of course, the 1/2 in front. So this is going to give me 1/2 e to the 5 plus 2x all plus c, putting back in my u. Let's try the integral of the secant squared of x e raised to the tangent of x with respect to x. And so when I look at this, I see all kind of things going on here. In terms of a basic rule, it's not even going to be possible because I see that I have trigonometric functions and I have an exponential function, and there's just no way that any of those don't go together, at least in my basic rules. So we'll try for a u substitution. And so far, we found with exponential functions, sometimes it's good to go ahead and look at letting u be equal to the exponent. Well, if u is equal to the tangent of x, then the u prime that I need to go with that is going to be, of course, the secant squared of x. So once again, I have my e to the u, and I have my u prime, and when I integrate that, I simply get an e to the u plus c, or in this case, an e to the tangent of x, all plus c. Okay, let's go ahead and do a comparison on this one. I want to look at the integral from 0 to 1 of e to the x with respect to x versus the integral from 0 to 1 of e to the negative x with respect to x. And starting with the one on the left, this is just a basic rule. And when I integrate e to the x, I'm going to get back e to the x. Now, in this case, it is a definite integral, so we're going to use our bounds. Remember, we don't get a plus c. Now, the function here is the entire e to the x. So when I put in my top bound, I'm going to put it into the entire function. That is, I'm going to look at e to the 1. And then I'm going to subtract what happens when I put in the 0. And I get e to the 0. And I need you to be real careful with this because e to the 0 is not 0. It is actually 1. And so what we get here is e to the first power, or simply e minus 1. You got to be real careful when you're dealing with trigonometric and or exponential functions if you're going to put in zeros, because those things don't necessarily go to 0. All right, let's look at the one that I have on the right here, and let's see what happens to this one. This is not exactly an e to the x. And I'm going to show you the kind of long way of doing it, and then we'll talk about what happens in a minute to make it a little bit easier for you. But this is not a basic. This is actually going to be a u substitution, and I'm going to let u be the angle, which is a negative x. If that's the u, then the u prime that I need here is a negative 1, or simply a negative. So here is my e to the u. I need my u prime, which is just going to be a negative 1. That means I will need to multiply on the outside by the reciprocal, which is a negative 1. And so that gives me my u prime times e to the u. Remember that anything on the outside carries down. So the negative carries down, and we simply get e to the u, or e to the minus x, which I can then look at between 0 and 1. Now we'll put the bounds into that in just a minute. Let me give you a little sidebar here, and I'm going to come down to the bottom of the page and show you this. Remember that our basic rule makes a lot of sense to us because integration and differentiation are opposite processes. So when I take the derivative of e to the x, of course I get e to the x. Well, let's look at e to the minus x. When I take the derivative with respect to x of e to the minus x, what do I get? Well, I simply get minus e to the minus x. Then if I take that derivative again, I simply get plus e to the minus x. In other words, every time I take the derivative of that thing, it simply changes signs. Well, based on that, look back up here at our problem we just worked on. That's exactly what happens when we integrate it. If I integrate an e to the minus x, I'm going to get a negative e to the minus x. If I integrate a negative e to the minus x, I'm going to get a positive e to the minus x. So it's going to do the same thing that differentiation did. So just an easier way to look at it. You don't actually have to write out the u substitution. Once you kind of get that, then you can just come in and put what it is. Integral of e to the minus x is minus e to the minus x. Now, I'm going to go ahead and put in the bounds. I typically don't like to put my negatives in, so I'm going to leave that out. However, before I put in these bounds, what I want you to notice is that those are positive values, and if I put them into here, I'm going to have e to a negative exponent, and I can't calculate a negative exponent. So before I do this, I'm going to rewrite this as 1 over e to the x, which I'll look at between 0 and 1. Now again, my personal preference is to leave those negative on the outside, which is what I'm going to do. Then I'm going to take this, and I'm going to put in the top bound, which is 1, and then I'll subtract what happens when I put in the bottom bound, which is 0. And so this gives me minus a 1 over e. Remember, e to the 0 is 1. And so this is going to give me a minus 1 over e plus 1. Okay, let's try one more of these definite integrals. Kind of like to see these. And so this, I believe, is our number 4. I'm not sure if I'm off on the numbering, but that's okay. Let's try the integral of the natural log from the natural log of 1, to the natural log of 8 of e to the x over 3 with respect to x. And let's do a little bit of sidebar here, just so we make sure we're clear on that. X over 3 is the same thing as 1/3 x. And the reason that works is because, remember that x is just x over 1. So if you multiply the tops and the bottoms, you'll get back to where you started. And we can always do that. And we've seen that in the past. We can do that with our fractions here. If I have 2x over 3, I can rewrite that as 2/3 x. They're one and the same. So my point being, in this case, I might want to rewrite this as the integral from the natural log of 1 to the natural log of 8 of e raised to the 1/3 x with respect to x, because I think, again, seeing those numbers in front makes it a lot easier to figure out what's going on. For me, at least, anyway. So I start by looking at this and saying, okay, this is not going to fit a basic rule, but I'm going to try a u substitution. So far, the angle's been working out pretty good. So let's let u be equal to, I'm sorry, not the angle, the exponent. So let's let u be equal to 1/3 x, which means the u prime that we're going to need for that is a 1/3. This then is my e to the u. I need a 1/3 in here, no problem. I'm going to multiply on the outside by the reciprocal, which in this case is going to be a 3. Anything on the outside carries down. And of course, once we integrate our u prime times e to the u, we simply get back e to the u, or e to the 1/3 x, which we can then look at between the natural log of 1 and the natural log of 8. Now, again, when you put this in, make sure that you do understand that the function is the entire exponential. It's not just put the stuff in the exponent on the top, it's the whole thing. So this is going to give me then the following. I'm going to start by putting in the top bound, which is 8. That's going to give me e to the 1/3 times the natural log of 8. Minus what happens when I put in the bottom bound, which is the natural log of 1. So I get e to the 1/3 times the natural log of 1. And then I'm going to start dealing with this, because those, of course, are not acceptable answers. But let's start by looking at this. The natural log of 1 is 0, and anything times 0 is 0. So this second piece here, and let me kind of bring this stuff down for a minute. I'll deal with that first one in a second, is just going to give me an e to the 0, which I understand is a 1. Now, remember that exponentials and natural logs are inverses of each other, which means they will cancel each other out as long as they are exactly side by side. Again, let me do a little side note here. If I have e raised to the natural log of x, then the e and the natural log will cancel out, and I simply get an x. Similarly, if I have the natural log of e to the x, again, they're side by side with nothing in between them, so they cancel out, and I get just an x. Well, the problem with what I have here is the e is not sitting directly next to the natural log. I have to somehow get rid of this 1/3. And the way we do that is using our properties for natural logs. Remember, in your notes, I have put some videos too, so that you can review your properties of natural logs. Those numbers in the front become exponents. So this is equivalent to e raised to the natural log of 8 raised to the 1/3 power, and 8 to the 1/3 power is 2. So this is 3 times e to the natural log of 2 minus e to the 0, which is 1. And now that these functions are sitting directly next to each other, they do indeed cancel, and we get 3 parentheses 2 minus 1, because that's what this quantity comes out to be, is simply 2, and that's 3 times 1, which is 3.